Alright guys, so the first thing that I'm going to do is I'll create a geometry network. I'll call it sim and I'll change the color here. Come to the viewport here and I'll change it to front view. I'll press D and come to the background and I'll pull up an image here. Alright, so that will be placed in our background in our front view. So we have our heart here and we will be tracing this. So I'll use a curve node here, and with the help of this curve node I'll be tracing this heart. Okay, trace the boundaries. So I'll keep one point here and I'll be pulling it up here. So if you have used the pen tool in Photoshop, then this is going to be easy for you. That's how it is going to work. And I'll pull it here and actually wait, I'll undo it. I'll control Z it and I'll put a point here, pull it up, pull point here, pull one point here and pull, and then I'll just join it here. Okay, connect. Yes, so now we have our heart shape and I can adjust this points here, this arrows, to fit, to align our curves here properly. Okay, so this looking nice. We have our heart here. What I'm going to do next is, first I'll just remove the heart image and come to perspective mode. Okay, so the second thing that I'm going to do is I'll create a resample node and I'll resample this. I'll use the target size to 0.025. Okay, so we have our heart here. Next I'm going to do is I'll use a poly extrude node and I'll extrude this heart. So maybe 0.322. That's what I used in my example, so that is looking good. And divisions needs to be 10. Okay, all right. So another thing, just turn on the output back, and the next thing I'm going to do is I'll use a transform node and I'll just decrease the uniform scale here to 0.7 or 0.75. So yeah, okay, this looking nice. Let me use a ISO offset node here and I'll change it to 50, uniform sampling divisions to 50. I'll now use a scatter node to scatter some points. Okay, change the force count to 25. Change the force count to 25. Play with the global seed here. I'll change the global seed to something like 39, or actually 46 is looking good. I want a quite a distance between these points. All right, I do not want them to be closer. Maybe I'll play with the value more. Yeah, the 46 was fine, so we'll keep that. The other thing that I'm going to do is I'll use a copy to points node and we will copy a sphere on all these points. All right, so I'll connect the copy to points node to our scattered points, and the geometry to copy is going to be sphere. So I'll change the sphere to polygon and I'll change the frequency to 10. So that's what we want. So a sphere is connected, scattered on all our points like this. We have copied a sphere on all our points, and I need to change the scale, so I'll use a scatter and align node. I'll connect both the inputs here of the scatter and align to scatter, and I'll change the mode to add attributes to existing point cloud. All right, let's change the minimum radius to something, maybe 0.23, and let's change the maximum radius as well, so maybe 3.6, 2.6, 3.66. yeah, that is looking nice. Maybe I'll have to use the uniform scale to 0.3 and 0.35, 3.4. Yeah, it is looking fine. Let's play with the, yeah, this is looking nice. And yeah, we have our spheres which are all sitting quite sitting at a space from each other, so that's what we wanted. uh, Maybe I'll rotate it also. So this looking okay. So the next thing that we need to do is I'll use a Vellum balloon configuration here, and the Vellum balloon configuration gives us Vellum cloth constant and the pressure constant. I'll change the group type to points in both the constants here. Come to cloth constant, and the cloth constant provides us with two important properties of cloth: stretchability and the bendability. In the stretch section we control the stretchability, so we want it to be less stretchy, so change the stiffness to 1e plus 8, and the rest length scale controls the distance between the 2 points in simulation. Okay, the bend section controls the bendability of the cloth. I'll change the stiffness to 0.0001, and yeah, do I have to change anything else? Okay, so we'll come to the pressure constraint now, and the pressure constraint maintains the pressure and generates the pressure. So stiffness maintains the pressure and rest length scale generates the pressure. So I have kept the stiffness to 1e plus 7, and the rest length scale, we want to generate some pressure here, so it is at 10. We'll just use our Vellum solver here. We'll connect it. Okay, so Vellum solver, and I do not want, I'll change the substeps to 2, and I do not want any forces here, to 0. Okay, so what we need is we need a collision here, collision geometry. And for the collision geometry, we'll definitely use our heart shape that we generated before. So let's bring that here, and where is it? Yeah, let me just align it properly first. So we'll take the poly extrude node, and we'll use a transform node, sorry, remesh node, and then we will just change the target size to 0.1, so we have good geometry, enough points here. Then we'll use a transform node here to wait, I'll just template the heart here, and as you can see that the heart shape is colliding with our spheres on the first frame itself. So I'll change the positioning here a bit like this, but we'll have to change the size of the heart, so I'll change it to 1.3 uniform scale and play with the position here. So okay, the spheres initially are not colliding with the geometry, and that is looking nice. So we will animate this. Okay, this heart shape, this heart transformation. At frame 1, I'll just keep it at 1.3, and then at frame 24, I'll bring the uniform scale to something like 0.1 or 0.2. 0.2 is looking fine. So okay, let me just put a keyframe here, and we have our collision geometry. Okay, we'll connect this collision heart geometry with our Vellum solver like this, and finally we can run the simulation and see what is going to happen. So let me just turn off the backplate, and I'll save this file, and let's run this. Okay, so the spheres that we generated are behaving like a balloon, and they are colliding with our heart-shaped geometry that we created. And at frame 18, 19 it is looking too harsh, but at frame 18, let me just check it properly. We'll use a Vellum post process after the Vellum solver, and let me just increase the spatial blur to something like 0.459. Okay, so now the geometry is looking nice, but at frame 19 there are some collisions, inner collisions, self collisions there. At frame 18 it is looking nice. So okay, we'll be using the frame 18 as our base frame for our next sim. So that is that. The other thing that we are going to do is we'll create another simulation for this, where we will be beating this hard. What I mean is, we'll create an effect in our Vellum solver with the help of the wrestling scale, so that it looks like this heart shape is beating. Alright, and we'll be doing that in our next shape. But before that, at the Vellum post process, I turn the loop to 1 and it is looking nice. But how many points are there after the loop? Let me just turn on the loop, and I think we'll be fine without a lot more geometry. This geometry is enough. So I'll just use a time shift node, and I'll just freeze the time frame at 18. So we have frame 18 here, and I'll use a file cache node to save it to disk. Okay, so come to file cache and turn off the time dependent cache, and then save it here. So we have our geometry here, which we'll be using as our base for our heartbeat geometry that you can see in our preview here. I'll use an attribute delete node, and I'll just delete everything with the help of a star. I'll use a group delete, and we'll delete everything. So I'll use a star here as well. Okay, it's looking nice. So what we are going to do next is I'll use a attribute triangle. As you can see in our preview, that the heart is beating initially. And then it starts inflating, or it starts imploding from the outside towards the center. Okay, and that's what we are going to create with the help of attribute triangle and distance function. So let's create an attribute triangle. I have the attribute triangle here, and then I'll create a float, and I'll create a float variable called dist, and it is going to be equal to our distance function, and we'll be running that distance function from 0, from the center of the world, to all the points and their positions. So 0 to the position of all the points. Okay, that is our distance function. So dist is equal to, I want to fit the distance that we will be getting from this distance function, but before that, to find the values for of that distance function, let's create a attribute f@dist is equal to dist. So we have a dist attribute, and finally we can finally see the values of the distance function here in the geometry spreadsheet. The maximum value is 0.3 and the minimum is 0.001. So let's just fit those values. So dist is equal to fit, let's fit dist 0. The minimum value is 0.0301, and the maximum value is 0.3, and we will fit that into 0 and 1. Okay, so the closest value for the points with the help of the distance function we got was 0.1, and the farthest was 0.3, and we have changed that, we have fit that into 0 and 1. So all the points which are near to the center will have a value of 0, and the points which are further will have a value of 1. Okay, so dist plus equals, I'll just create a offset here, dist plus equals chf offset. Let me just turn it on, and if I change the offset value here, you can see I'm adding the offset value to our distance attribute. Come to the edit interface and we'll change the offset range from 0 to 1 to -1 to 1. And now if we change the offset value, you can see if we keep it at -1, then everything is going to be negative or below 0. And if I change the offset value to 1, then it will be increasing. So at frame 6, I'll keep the offset value to -1, and at around frame 160, I'll keep the offset to 1, thus animating it. And this way, as the animation progresses or as the frames pass, the distance attribute will be going from 0 to 1, okay, from outwards to inwards. And one more thing that we can do here in the wrangle is we can clamp the values here, because when we add the offset, the values are going below 0 and above 1. So dist is equal to clamp, and we'll clamp the dist to 0 and 1. And now when we run this animation, you can see initially everything is black, and then it goes to 1, and then it goes to 1. After the attribute triangle, I'll create a attribute remap like this, and we will remap the dist attribute here. Okay, and I want to make it a bit sharp here, so let's just add some contrast in the ramp here. So I'll bring the point here to around 0.03. Thus now when we run the animation, you can see when we visualize the dist attribute, it is more sharp. Okay, before it was like this, it was a bit dull, and now it's quite sharp. So the distance attribute will be coming from outwards to inwards, the value will be increasing, and we'll use that in our Vellum simulation to inflate all these balloons here, these objects here. Let's use a for each connected piece to further improve our attributes here, to further improve our attribute setup. For each connected piece, and inside this I'll use a attribute promote node, and we will promote our dist attribute from point to detail. Okay, so come to the original name here, use dist, and we'll promote point to detail, and I'll keep the promotion method to maximum. I'll use another attribute promote from detail to point, and I'll keep the promotion method to average. And now when we run the animation, you can see that one by one they are turning from black to white. Okay, they are turning from black to white, or the value is increasing from 0 to 1 by 1. Okay, and that's what we wanted, like this. Maybe I'll change the frame range for the attribute triangle here, for the offset here, and you can see this is just looking nice. Okay, this is looking nice. And after this, if I run the animation, it's happening too quickly for me, but I think this will work fine. So after this, we'll be creating a null, and I'll call it out geo. Just turn it off, connect this out geo, and now I'll create a group node which will consist of all the points here. So let's change the group type to points, and we will call this everything. After this, I'll be creating a Vellum balloon configuration which will give us two important nodes, which is Vellum cloth constant and the pressure constant. Let's change the group type to points in both of them. The Vellum cloth constant provides two important properties for our mesh, which is the stretchability and the bendability. Let's come to strut section and change the stiffness here. and we'll also change our bend stiffness here. Okay, or maybe I'll just keep it like that only. We do not need to change the bend stiffness, which controls the bendability or foldability of the object. Okay, the pressure constant controls and maintains the pressure inside a geometry. The stiffness maintains the pressure, and the wrestling scale controls or generates the pressure. Okay, so I'm changing the stiffness here to 1e+7, and I'm also creating an output group which is called stretch pressure, with the help of which we'll be able to manipulate our wrestling scale or the entire stretch section of the pressure constraint inside our Vellum solver. So that is important. After this, I'll be creating a Vellum constraint, and we will change the constant type to pen to target and change the group type to points here, and we will apply this constant to everything. Let's change the come to pen to animation and change the pen type to soft. Okay, so the pen to target constant controls whether the object is going to take participation in the simulation or it will keep its original position. So higher the stretchability or bendability, that means it will keep its original position, and lower the stretchability or bendability, and then it will take participation in the simulation. Okay, now we'll use a Vellum glue constraint, and with the help of the Vellum glue constant, we will make sure that all these separate geometries will be attached to each other. They'll be glued to each other, and they will not separate from each other. So I'll keep the